This is homework 4, part A, and I'm going to be explaining the ways to estimate diffusion coefficients for vapor and liquid in binary mixtures, and then how we use the Bingay's formula to use the Bingay's formula to in conjunction with the Stokes-Einstein equation. So first, for vapors, we use Herschenfelder's equation. And this equation is based on the Chapman-Encogs theory. Yeah. And it's used by, so you use it by the molar weights. And the theoretical molar weights and collision diameters. And the answers range in to the -5 meters squared per second. And then for vapors, for gas or liquids, we use the Stokes-Einstein equation. And to calculate this, we use it as a molecule, a spherical molecule. Going through a viscous liquid. And this is, theoretical, and the values range from 10 to the -9th meters squared per second, which is way smaller than the Herschenfelder's equation. Alright, so now we're going to explain the conjunction between the Bingay's and the Stokes-Einstein equation. So the Stokes-Einstein gives the diffusion for infinite dilution, which means that solution A is very small and solution B, so it's very, very dilute. But in real mixtures, like this is it's theoretical, so like in real mixtures, like concentration like matters. So that's when we use the Vinge oh my goodness, yeah, equation. So yeah, we use the Vinge's equation to symmetricize, so we can use this to interpole over a longer or bigger concentration and calculate it that way. And after we use this to symmetricize and interpolate over larger concentrations, we get diffusion over 1 to 2, so like A to B, and this is Maxwell-Stefan diffusivity. This is homework. All right, so now we're going to derive, this is homework for A part 2. And now we're going to derive the equation for continuity. And so we're going to think of doing this over a small section. We're going to call that delta Z. So the general equation is accumulation is equal to in plus out, in minus out, plus generation. So this equation is going to be a small area A with a thickness of delta Z. And that is a gradient of concentration of A. This is like two different compounds, A and B. The concentration of A times the area times delta Z over the gradient of time. is equal the molar flux of A integrated over Z times A minus the molar flux of A over the integration of Z plus delta Z. So like that's from the bottom point to the top point. Plus area plus RA times the area plus delta Z. So now we're going to divide by the volume, which is the area times delta Z, and then integrate delta Z going to 0. So then that leaves us with the gradient of concentration A over time is equal molar flux of A divided by delta Z plus RA. And then because this is steady state, this goes to 0, so then that leaves us with this molar flux of A over dz plus RA. So then that leaves us with RA being equal to the molar flux of A over dz. And that is the equation for continuity. So now I'm going to explain how equimolar counterdiffusion arises at vapor-liquid interfaces when enthalpy of vaporization is independent of composition. So this occurs at vapor-liquid interfaces. Like distillation. When the enthalpy of vaporization is constant. So when 1 mole of species A is condensed, it releases energy of delta change in molar enthalpy of vapor A, species A. When 1 mole of species A condenses, it releases energy as molar enthalpy of vaporization of A. So then this is exactly enough energy that species B can enough energy to vaporize species B to release a certain amount of energy of vapor B. So because it's constant, enthalpy is constant, there's no change. That means that molar flux net is equal to molar flux of A plus B. So then that gives us the molar flux of A being equal to the negative molar flux of B. This is homework 4, part 4. Part 4, homework 4A, part 4. So now we're going to look at molar flux relationships and reactions. And this is simply calculated through stoichiometry. Because with reactions, like, they have to go somewhere so to remain constant, steady state. So if we're looking at species A going to 2B, 1 mole of species A is going to the positive or the negative direction because it's going up to, we're going to think of it going like, we're going to think of it as like a block. This is B, A. This is the positive direction. This is the negative direction. So 1 mole going in the negative direction. And then we have 2 moles of species B going in the positive direction. So the net molar flux is equal to A, net molar flux of B. So the relationship between A and B is A net molar flux of B is equal to negative 2A molar flux of A. So then we plug that in. So and this relationship is equal to negative molar flux of A. So then now if we're thinking of 3A to B, 1B, so 3 moles, species A, going in the negative direction, and 1 mole, species B, going in the positive direction. So this relationship can be represented as net molar flux of B is equal to 1 1/3 negative molar flux of A, negative 1/3 of molar flux A. So molar flux net again is equal to A plus, not mu, B, which then can be wrote as and so the net molar flux is equal to 2/3 of the net molar flux of A.